These days, I don't know what I would do without Facebook and Twitter. It's so easy to keep track of all of my friends.
Yeah, that's a good point. I use Facebook a lot to share photos with my friends.
I wonder sometimes, it seems like a lot of my friends have more friends than I do.
Yeah, that's a good point. Maybe my friends do have more friends than me.
Hi, I'm Katrina.
Hi, I'm Amy.
And we're here today in Cambridge, Massachusetts to ask people this one simple question. Do you have more friends than your friends do?
Wow. I guess my friends probably do.
I think it probably depends on the ecosystem that you actually have, who you're connected to.
Probably my friends. I like a tight-knit group as opposed to a numbers guy.
I feel like I have an equal amount. I don't really count friends as like a competitive game.
Katrina, I don't understand. Why would I expect to have more friends than my friends do? Shouldn't we have about the same number of friends? Shouldn't it be about a toss-up as to who has more friends?
Let's ask the class. Class, what do you think? Do you have more friends than your friends do on average, or fewer? Discuss with your neighbor, the rest of the class, and then report back to us. So class, what did you decide? At this point, it's probably hard for you to decide whether you have more friends than your friends do, on average. We can start to answer this question by looking at some data. What data, you ask? Social networks.
Online social networks give us a way to collect data to answer questions about relationships between people. For a particular example, we can count the number of friends we have on our online social network, count the number of friends our friends have, and compare. This won't give us perfect information. We won't be able to count people who don't have online social network accounts, and we might include people that we don't truly consider friends. But it's a good start.
Let's try it. Here's my social network. As you can see, I have 4 friends. Let's look at the first friend's network. She has 5 friends. Now, let's look at the second friend's network. He has 3 friends. The third has 4 friends, and the fourth has 5 friends. So in this case, I have 4 friends, and on average, my friends have 5 plus 3 plus 4 plus 5 divided by 4, which is equal to 4.25 friends. So my friends do average more friends than I do.
Now it's time for you in the class to try. Using the provided datasets, determine how many friends you have and how many friends your friends have.
Once you figured it out, do your friends typically have more friends than you do? Well, what did you find out? Surprisingly, in most cases, a person's friends have more friends than they do. But why is that? There's an intuitive way to look at this question. If, on average, my friends have more friends than I do, that means that I'm friends with a lot of popular people, or at least more popular than me. And that makes sense. A popular person is more likely to make friends. That's what makes them popular in the first place. This intuition is helpful in understanding our result. But what do you think, Amy? Could we be more rigorous?
I have an idea. Let's get data from everyone's social networks. We could figure out how many friends each person has and compare that to the average number of friends that their friends have and see how frequently the first number was less than the second.
That's a good start. But think about how hard it would be to collect all of that data, and then to do all of those calculations. Plus, every time the social network changed, we'd have to do everything all over again.
Good point. I guess that's not really feasible.
What we'd really like is a way to explain this phenomenon mathematically, and in a way that doesn't depend on the exact social network in question.
Can we do that?
It turns out we can. The type of math that we'll use to prove this is known as graph theory. Graph theory is useful when we're faced with a problem that involves relationships or connections between objects. Here, the objects are people, in particular us, our friends, and our friends' friends. 2 people are connected if they are friends.
I know some graph theory. The objects of a graph are called vertices, and the connections are called edges. 2 vertices have an edge between them if they are connected. If 2 vertices A and B have an edge between them, we often say that the edge touches A and B.
That's right. Now let's see how some of our social network concepts translate into graphs. Let's imagine a graph of 6 people: Alice, Bob, Carla, Dan, Eve, and Fred. If any 2 people are friends, we'll put an edge between them. Suppose we have the following friendships. Alice is friends with Bob, Dan, and Fred. Bob is friends with Alice, Carla, Dan, Eve, and Fred. Carla is friends with Bob and Dan. Dan is friends with Alice, Bob, Carla, and Eve. Eve is friends with Bob and Dan. And Fred is friends with Alice and Bob. Here's the graph.
Now it's your turn to try. Using the provided datasets, get into groups and practice making your own social networks, using the pieces of string to form the edges. How many friends does each person have? How many friends do each of your friends have? To figure out how many friends a person, let's say Alice, has, we first find the vertex that represents the person and then count the number of edges that touch the vertex. In this case, it's 3. Alice is friends with Bob, Dan, and Fred. This number, the number of edges touching a vertex, is known as the degree of the vertex. So the number of friends Alice has is the same as asking for Alice's degree in the graph. We'll refer to the degree of vertex V as dV.
What about the average number of friends that Alice's friends have?
We'd look at Alice's vertex and all of the vertices connected to it. We'll count the number of edges that each of those vertices has, the degree, and then average those numbers.
In our example, Alice is connected to vertices B, D, and F. The degree of B is 5, the degree of D is 4, and the degree of F is 2. So on average, Alice's friends have 5 plus 4 plus 2 divided by 3, which is equal to 3.66 friends each. What we see here is that, indeed, Alice has fewer friends than her friends do.
We could keep doing this for every person in the graph, just like you did with the datasets in the previous activity. We'd find that most people in the graph, but not everyone, have fewer friends than their friends do.
Remember that what we really want to do is make a broader statement that isn't specific to any particular person. This is where the averaging comes in. We want to prove that the average number of friends that people in a social network have is less than or equal to the average number of friends that their friends have.
Notice that we're not proving that the number of friends that any specific person has is less than or equal to the average number of friends that their friends have. We've seen cases where that's false.
To prove that the average number of friends that people have is less than the average number of friends that their friends have, we need to calculate two quantities: the average number of friends a person has and the average number of friends a person's friends have. Can you figure out these two quantities for our example social network? The second quantity might seem strange. After all, why should the average number of friends that a person has be different than the average number of friends that their friends have?
Katrina, should we give them a hint?
Sure.
Here's a hint. Think about the first quantity we calculated, the number of friends a person has. What is this formula when we apply it to the number of friends a friend has?
Instead of calculating the exact numbers for these values, try to leave your formulas in terms of the degrees. So dA, dB, etc. Let's see what you came up with. The first quantity is the average number of friends that a person has. To figure out the average of a group of n numbers, we simply add up all of the numbers and then divide by n. Since we're interested in finding out the average number of friends that a person in our graph has, we'll add up the number of friends that each person has and divide by the total number of people in the graph. Since the number of friends a person has is equivalent to the degree of the vertex that represents that person, whenever we see the number of friends A has, we can replace that with dA. We can do the same for B, C, D, E, and F. So the average number of friends a person in our example has is dA plus dB plus dC plus dD plus dE plus dF, all divided by 6. For our graph, this is 3 plus 5 plus 2 plus 4 plus 2 plus 2, all divided by 6, which is equal to 3.
Wait, I know a faster way to calculate that. If we add up the degree of every vertex in the graph, we'll end up counting each edge twice, one for one vertex that touches it and once for the other vertex. Now we can rewrite that formula to be 2 times the number of edges in the graph divided by 6.
That's right. The sum of the degrees in the graph is twice the number of edges. Now let's move on to the second quantity, the average number of friends that a friend has. Even though this quantity might seem strange, we can calculate it using the same formula for the average. We'll just add up the number of friends that all of the friends in the graph have, and then divide by the total number of friends.
Let's start with the numerator. What's the total number of friends that friends in this graph have? We can go through person by person. The number of friends Alice's friends have, plus the number of friends that Bob's friends have, plus the number of friends that Carla's friends have, plus the number of friends that Dan's friends have, plus the number of friends that Eve's friends have, plus the number of friends that Fred's friends have.
Let's start with just the number of friends that Alice's friends have. Alice is friends with Bob, Dan, and Fred. Bob has 5 friends, Dan has 4 friends, and Fred has 2 friends. So Alice's friends have 11 friends altogether. But remember, another way to say the number of friends Bob has is just dB. So another way to write the number of friends that Alice's friends have is dB plus dd plus df.
Now let's move on to Bob. Bob is friends with Alice, Carla, Dan, Eve, and Fred. Alice has DA friends, Carla has DC friends, Dan has DD friends, Eve has DE friends, and Fred has DF friends. Altogether, Bob's friends have DA plus DC plus DD plus DE plus DF friends.
We can do the same thing for all of the other people, turning the numerator of our fraction into dB plus dd plus df plus dA plus dC plus dd plus dE plus df plus dB plus dd plus dA plus dB plus dC plus dE plus dB plus dd plus dA plus dB.
The denominator of this fraction is easier to simplify. We start out by noticing that the total number of friends in this graph is equal to the number of friends that A has, plus the number of friends that B has, plus the number of friends that C has, plus the number of friends that D has, plus the number of friends that E has, plus the number of friends that F has. Since another way to say the number of friends that A has is dA, this quantity is the same as dA plus dB plus dC plus dd plus dE plus dF. Now we have a formula for the second quantity. For our graph, this works out to 11 plus 13 plus 9 plus 12 plus 9 plus 8 divided by 18, which is 3.44. For this particular graph, we got the expected result. The average number of friends that a friend has, 3.44, is greater than or equal to the average number of friends that a person has, which was 3.
But this doesn't tell us anything about what happens in a general social network. Can you use the formulas that we came up with for this specific graph to figure out the formulas for a more general graph? Welcome back. Since we want to figure out these quantities for a general graph, not just our specific example, let's see if we can use the formulas that we came up with to gain some insight. First, you probably noticed that the average number of friends is the sum of the degrees of all of the vertices in the graph divided by the total number of vertices. We'll write that as the sum of the degrees for each vertex v divided by n, and we'll use n to refer to the total number of vertices in the graph.
And remember from before, we can actually write that as 2 times the number of edges in the graph divided by n. What about the average number of friends that a typical friend has? This one is a little trickier. The denominator of the formula we came up with was the sum of the number of friends each person had, i.e. the sum of all the degrees in the graph. Let's rearrange the numerator by grouping like terms together. dA plus dA plus dA plus dB plus dB plus dB plus dB plus dB plus dC plus dC plus dd plus dd plus dd plus dd plus dE plus dE plus dF plus dF. This equals 3dA plus 5dB plus 2dC plus 4dd plus 2dE plus 2dF. Hey, look! dA appears 3 times in the numerator, and it happens that for our graph, dA equals 3. And it works for dB too. dB appears 5 times in the numerator, and dB equals 5. At least for this example, it looks like we could rewrite the numerator as dA times dA plus dB times dB plus dC times dC, plus dd times dd, plus dE times dE, plus dF times dF. Multiplying a number by itself is the same as squaring the number, so we can also write that as dA squared plus dB squared plus dC squared plus dd squared plus dE squared plus dF squared. This is the sum of the square of each vertex in the graph, which we can write as the sum of dV squared for each vertex v.
Will this happen with every social network, or did we just get lucky with this one? Let's think about how we calculated this value. We added up the number of friends that A's friends had, plus the number of friends that B's friends had, etc. A's friends are B, D, and F, so the number of friends that A's friends had was dB plus dd plus dF. B's friends are A, C, D, E, and F, so the number of friends that B's friends had was dA plus dC plus dd plus dE plus dF. Amy, how many times have dd and dF shown up so far?
Twice. Once when we calculated the number of friends that A's friends had, and once when we calculated the number of friends that B's friends had.
And how many more times will dd show up?
2 more times. Once when we calculate the number of friends that C's friends have, and once when we calculate the number of friends that E's friends have. This is because D is friends with C and E in addition to A and B. So dd appears 4 times in the summation, each time we calculate the number of friends that one of D's friends has.
Correct. And what about dF?
dF, on the other hand, won't show up again. F is only friends with A and B, so it won't show up in the summation for any other person.
That's right. Using this logic, we can see that for a vertex v, dv occurs dv times in the numerator, once for every friend that v has. Now, our original problem is the average number of friends that a typical friend has greater than or equal to the average number of friends that a typical person has, is the same as asking if the sum of the degrees squared over the sum of the degrees is greater than or equal to the sum of the degrees divided by n.
To build up some intuition before we get to the proof, it's helpful to think about the most extreme examples of social networks. For instance, what's the most extreme graph you can think of in terms of a person's friends having more friends than they do?
What about the second extreme? Are there social networks where people never have fewer friends than their friends do?
Work with a partner to come up with examples of these 2 cases. One where almost everyone in the graph has fewer friends than their friends do, and one where no one has fewer friends than their friends do.
So what did you come up with? The first extreme is one where one person is friends with everybody, and everyone else is only friends with that one person. There, the number of friends that most people have is 1, and the number of friends that most people have is n minus 1. Here, n minus 1 of the people have 1 friend, and the nth person has n minus 1 friends. This means that the average number of friends that a person's friends have is the sum of 1 squared, n minus 1 times, plus n minus 1 squared, all over the sum of 1 n minus 1 times plus n minus 1. With some simplification, we can see that this equals n over 2.
The other extreme is one where everyone has the same number of friends. One way for this to happen is for everyone to be friends with everyone else.
In the first extreme, the number of friends that people had varied. Most people had 1 friend, but then one person had n minus 1 friends, and n minus 1 is usually much greater than 1. In the second extreme, the number of friends that people had did not vary at all. In our example, everyone had n minus 1 friends. Since the way in which the number of friends varies seems like it might be important, let's make that notion more precise.
We can talk about the way in which the number of friends vary in a mathematically precise way. Since the number of friends that a person has is the degree of their vertex in the graph, what we're really studying is the way the degrees of the vertices in the graph vary. The way that we can measure this is by calculating the variance of the degrees. The variance of a set of numbers measures how spread out those numbers are by calculating how far away each number is from the average, or mean. Remember that the mean mu of a set of numbers is the sum of the numbers divided by n. If all of the numbers in the set are identical, the variance is 0. As the numbers spread out and get further away from the mean, the variance increases.
The variance, sigma squared, of a set of numbers is defined as the sum of the squared differences of each number from the mean, all divided by n. When we're talking about the degrees of a graph, the mean will be equal to the sum of the degrees divided by n, and the variance will be equal to the sum of each degree minus mu squared divided by n. We know that our goal is to show that the sum of the degrees squared divided by the sum of the degrees is greater than or equal to the sum of the degrees divided by n.
It's difficult to work with these equations entirely as summations, so we're going to replace some of them using our formulas for mu and sigma squared. We can start by using the definition of mu and substituting directly, so that our inequality becomes the sum of the degrees squared over the sum of the degrees is greater than or equal to the mean.
From the definition of mu, we can also see that the sum of all of the degrees is mu times n. This lets us make another substitution. Now our inequality is the sum of the degrees squared over n times u is greater than or equal to mu. We've gotten rid of all of our summations except for one. It doesn't look like our definition of the mean can help us, since there's no sum of dv squared. But what about the definition of variance?
This looks like it might be helpful, but we have the degree minus the mean squared instead of just the degree squared. Let's perform some algebraic manipulations to see if we can extract something more useful.
We'll start by expanding the summation. We can square each term. And now let's group all of the like terms together. We can simplify this again using summations, so we end up with 1 over n times the sum of dv squared minus the sum of 2 dv mu plus the sum of mu squared.
Well, we extracted out the sum of dv squared, but we have all these extra summations too. Let's see if we can get those to go away.
Since there are n vertices, the third summation becomes n times mu squared. We can also take 2 mu out of the second summation, so that we have 2 mu times the sum of the degrees.
Wait, our definition of mu is the sum of the degrees divided by n. We can apply that to the second summation in the formula.
That's right. Let's do it.
Now we have an alternate definition for the variance.
Even more importantly, from this definition, we can see that the sum of the degrees squared is equal to n times the variance plus the mean squared. Now we're ready to finish simplifying our original formula. Right now, we have n times sigma squared plus mu squared over n times mu is greater than or equal to mu. The two n's on the left side cancel out, and we can multiply each side by mu, giving us sigma squared plus mu squared is greater than or equal to mu squared. If we just subtract mu squared from each side, we're left with sigma squared is greater than or equal to 0. And this statement is true. The variance is 0 when every person has the same number of friends. Any other time, the variance is greater than 0.
Cool! Who knew we'd be able to prove a fact that I just observed amongst my friends and me?
Yep, sometimes we have to work through a lot of details to come up with a new insight, but it's worth it. So Amy, now we know the answer. Today we set out to understand why often our friends are more popular than we are. After exploring the question with data from social networks, we turned to graph theory.
That's right, Katrina. We saw how to model social networks as graphs and how to formulate our questions in terms of graph theory. In the end, we proved that, on average, the average number of friends that a person has is less than or equal to the average number of friends that their friends have.
It turns out we can prove all sorts of real-world phenomena with mathematics. When we're dealing with social networks, we often turn to graph theory because it models these types of problems so well.
Graphs can be used to model lots of other problems, too. They can be used to find methods for robots to navigate a room, to determine how to send traffic on the internet, and to help compute driving directions on a road.
That's right, Amy. Today we use them to show that usually our friends have more friends than we do. So proving, mathematically, that we can't all be popular. Hi, I'm Katrina, and I'm a lecturer here at MIT, where I teach in the Electrical Engineering and Computer Science department.
Hi, I'm Amy. I'm a graduate student here at MIT, and I'm studying computer networks.
Thanks for being interested in this Blossoms lesson. This lesson serves as a basic introduction to graph theory, as well as a review of mean and variance for discrete distributions, although we intentionally avoid using the word distribution throughout the lesson. We chose the friendship paradox specifically because it relates to social networks, which high school students use on a daily basis. Because it's paradoxical in nature, it's also an interesting question for students because it's not immediately clear why it's true.
This Blossoms lesson may be one of the first times that high school students see a mathematical proof. The proof of the friendship paradox uses mathematics that should be familiar to high school students: summations, algebraic manipulation, and manipulation of summations, means, and variances. The proof is interesting for a variety of reasons. First, it uses topics from statistics to prove a statement that is not obviously related to statistics. Second, students see that working through messy algebraic details can lead to proving some exciting facts.
Finally, by using the social network data that we provide, students get to experience how we can use real-world data to analyze and support a hypothesis. The prerequisites that are necessary for this lesson are an understanding of how to calculate the mean and variance of a discrete distribution and what those quantities represent, summation notation and an ability to manipulate summations, an algebraic manipulation and an ability to think about equations in terms of variables, not just numbers. In our examples, we often have equations that utilize the degrees of a graph.
Notably, the students do not need to be familiar with graph theory or continuous distributions before this lesson. We introduce them to all of the necessary graph theory topics, and we do not use continuous distributions.
In the first activity, students discuss whether they have more friends than their friends do. You may have them start off discussing in pairs or as small groups, and then open the discussion up to the whole class. Many students may not understand why we would expect these two quantities to be different at all, and that's okay. They don't need to understand the intuition behind the paradox at this point in the lesson. To wrap up the discussion, ask them how they might explore this question in a more scientific way. This leads into the activity using the fake datasets in activity number 2.
In activity 2, students use fake social network data to calculate the number of friends a person has, as well as the average number of friends their friends have. The data is divided into 2 social networks of 10 people each. So 10 students in the class will be using one social network, and 10 students will use the other.
Once they've done their calculations, you can ask the class how many of them had fewer friends than their friends did, and how many had more. There will be students with more friends than their friends. That's okay. But the class should conclude that most of them, however, had fewer friends than their friends did.
For the students who end up with more friends than friends of friends, have the class discuss what was unique about those students. They should come to the conclusion that the students with more friends than friends of friends are the more popular students. This should lead them to the intuition of why this paradox is true. You are likely to be friends with popular people. This is what makes them popular. And popular people have many friends.
Activity 3 is the first activity that uses graph theory. Here, the students create a physical graph amongst themselves, using strings to represent edges between friends. Then they calculate the number of friends and friends of friends. It's important when setting up this activity to make sure that the pieces of strings are long enough, otherwise the students will be all bunched together and it won't be clear who's friends with whom.
While doing the activity, students should conclude that the number of friends they have is equal to the number of strings they are holding. The number of friends their friends have is equal to the sum of the number of strings their friends are holding.
Once each group has completed this, you can bring the class together for a brief discussion about how they calculated these quantities.
In activity 4, students work in pairs to determine the formulas for the average number of friends a person has, as well as the average number of friends a person's friends have, for the social network in our example. The goal is for them to determine these formulas in terms of the degrees, rather than exact numbers, as it will help them with the 5th activity. If some students are having trouble, though, you might suggest that they calculate the quantities numerically first, and then see if they can take those calculations and put them in terms of the degrees.
A particular sticking point for some students may be how to calculate the average number of friends that a person's friends have. This is not the same as calculating the average number of friends that a particular person's friends have. If they understand well how to calculate an average, it should be possible to lead them to this quantity with the following hint. When we calculated the average number of friends a person had, we sum up the number of friends everyone in the graph has and divide by the total number of people in the graph. To calculate the average number of friends that a friend has, we sum up all of the friends that each person's friends have and then divide by the total number of friends. This will prevent them from dividing the numerator by n instead of by the sum of the degrees. This hint should also prevent them from calculating the average number of friends that each person in the graph has, and then averaging those numbers.
Once the students have completed this work in pairs, you can bring them together for a brief discussion of the formulas they got, and how they got them.
In Activity 5, the students extend their formulas from Activity 4 to a more general case. This activity can be done in pairs or in small groups.
Because they worked out the formulas in Activity 4 in terms of degrees, determining a general formula for the average number of friends should be straightforward. If students have trouble, though, you can ask them how they would calculate the formula if we added one more person to the social network example. And then what if we added another, etc. This should lead them to the idea that we are summing up the degrees of each vertex.
The second quantity might be trickier, as students might not immediately see that each degree is squared. For students who don't see that right away, it's okay for them to simply understand that we take each vertex and add the degrees of its connected vertices.
Once the groups have finished their calculations, bring the class back together for a discussion. In calculating the first quantity, for any groups who haven't expressed their formula in summation notation, make sure to point out how to do that.
For the second quantity, since some students may not have recognized that this is the sum of the squares of the degrees, ask the class to think about how many times each vertice's degree appears in the summation, similar to what Amy and I do at the start of segment 6. You can use the example from the video or do your own example to illustrate this. The students should notice that each degree d appears d times, but they might not understand why this happens. You can leave that explanation to us in segment 6.
In the final activity, students study extreme cases of the friendship paradox, the case where everyone has the same number of friends as their friends do, and the case where the variance in the number of friends is highest.
The first case is easiest to introduce. Have the students discuss what it would mean for one person to have the same number of friends as their friends did. It would mean that if they had X friends, then all of their friends also had X friends. Let the students come to the conclusion that one way for this to occur is for every person in the graph to be friends with everyone else, or just for every person to have the same number of friends. You can have them work in small groups or as a class to draw their own graph to figure this out.
As they are working on the first graph, they might explore how varying the number of friends people has influences this quantity. For instance, what happens when everyone is friends with everyone else, and then we add a new person to the graph who's only friends with one person? We see that the average number of friends people have is slightly less than the average number of friends a person's friends have.
You can have students keep adding vertices to the graph or taking edges away and exploring what happens. They should notice that if they take too many edges away, we're back to a case where the average number of friends is only slightly less or maybe even equal to the average number of friends. For example, a chain graph where every vertex is connected to the two adjacent vertices.
Through exploration, they should see that having one part of the graph that is highly connected and having the rest of the parts be sparsely connected increases the difference between the number of friends and friends of friends. An extreme example of this is having a single vertex v connected to all others and all of the other vertexes only connected to v.
If you enjoy this lesson, a related topic that you might choose to explore is the Blossoms lesson on selection bias, entitled, Is Bigger Better? A look at a selection bias that is all around us.